So last time we had given a general procedure for computing string amplitudes, okay, but the ingredients in that procedure was that we had to, the integrand involved correlation function of Riemann surface. Okay. But I didn't describe how one can compute correlation function of a CFT on a general Riemann surface. Okay. So I'll start with this question today. So the question that we'll be addressing is how to compute correlation function and the goal is to express this in terms of CFT 3-point function, in terms of sphere 3-point functions. And the sphere 3-point functions are of course the defining data for a CFT. So if you can express a correlation function on a general Riemann surface in terms of the sphere 3-point function, then you have a definition. Okay. Now I should also add that while this gives a definition of the correlation function on Riemann surface, often in actual calculation, okay, we don't really start from this, okay, because this is a very complicated procedure. Okay. One instead makes use of various analyticity properties of the correlation function, then operator expansion and so on. Okay, but this is an in principle definition of how to compute correlation function on a general Riemann surface. Okay. So for this, we'll is this visible up to this point? I mean, it's not blocked, right? I can. So we are going to compute. We are going to introduce basis states. In the CFT. So I'll introduce a set of basis state phi r, okay, and another set of basis states which I'll denote by phi r c, okay, and the condition that will be imposed that relates these two basis states is that the inner product between phi r c and phi s is delta r s. And this basis we introduce in all Gauss number. Okay. So the total Gauss number, so the Gauss number of phi r c is 6 minus nr, where nr is the Gauss number of phi r. Because the sum of the Gauss numbers of phi r and phi r c, phi of these two, okay, should add up to 6. Okay, 3 from the holomorphic sector and 3 from the anti-holomorphic sector. So based on this, we can write down the completeness relation. Which is sum over r phi r c is identity operator, okay, and there is another relation that I am going to write, which is phi r c phi r minus 1 to the nr okay, this is also identity. This minus 1 to the nr comes because this Yeah, maybe I should have written that. Okay. So this implies that if we take this inner product phi s phi r c, this is minus 1 to the ns. Okay. And the reason is that you have to switch the positions of phi s and phi r c. Okay. And if these are Grassmann odd, then you pick up a minus sign. Okay. And because the total Gauss number adds up to 6, if this is Grassmann odd, this is also Grassmann odd. If this is Grassmann even, this is also Grassmann even. So the sign that you pick up is minus 1 to the power Gauss number of phi s. Okay, that's why you get this. So the completeness relation will also have a similar factor over here. Is this clear? Now let's start with the simplest sphere amplitude, simplest amplitude is sphere 4-point function. And the way we had described the sphere 4-point function, if you recall, that we draw disks around the positions of the vertex operator. I call this the sphere S1, this is the sphere 2, S2. Okay. These are our disks D1, D2, D3, D4, and we have chosen a particular parameterization of the moduli space of sphere with 4 punctures, okay, which will be useful today, okay, which is that we take the transition functions to be Z1 equal to W1, let me call this A1 1, Z1 equal to W2 plus A1 2, Z3 equal to W Z2 and then finally Z2 minus A2 3 as Q over Z1 minus A1 3, okay, and Q is a modular parameter. That's the way we had introduced. This is the modular parameter. Okay. So from this perspective, if you want to write down the amplitude, okay, with this coordinate system, okay. Yes. These are, yeah. So on the sphere 1, I am taking the here. Oh, these ones. No, no. So A's I am calling. Okay, let me state the convention. So on the sphere 1, S1, the holes are around A11, A12, A13. On the sphere S2, the holes are around A21, A22, A23. Right? That's why we have taken these. So the third puncture is basically at Z2 equal to A21. Okay, and this is at Z2 equal to A22. Okay. So the only non-trivial modulus is here. Okay. And so from this perspective, the correlation function will be of the form V1 A11, V2 A12. Let me write this as f dot V3 of A21, f dot V4 A22. Okay, and I'll explain what F is. Okay. So F is the transformation. F of Z2 is A13 plus Q over Z minus A23. Okay, so let me explain what I have done. So this F of Z2, right? This is basically giving the relation between Z1 and Z2. Okay, so this relation I can write. Sorry, I should have written it the other way. Okay, which is the same. Let me write it here. Z2 minus A22 is Q over Z1 minus A23, 1, 3. Okay, it's the same relation. I just wrote it in the opposite way. Okay. So what this is saying is that Z2 is given by A23 plus Q over Z1 minus A13. That is what I am calling the function F. Okay, this function is the same as this. So this is telling us how to relate Z1 and Z2. Okay. All other relations are trivial because there is no transition functions across these don't depend on the moduli at all. Okay. So this is the reason why I can write it this way, because you see V3 is inserted at the point A21 in the Z2 plane. Okay. But if you want to rewrite this in the Z1 plane, we have to transform it by this function F. Okay, because F is what is giving you the relation between Z1 and Z2. Okay. Similarly, V4 is inserted at A22 in the Z2 plane. Okay. But when you convert it to Z1 plane, you have to again transform by this function F. Okay. So this is the correlation function on this, on the sphere, okay, 4-punctured sphere. Is this clear? Right? And this is the way we had introduced the modulus earlier. Okay, we just the transition functions are the non-trivial dependence of the transition function on the moduli are all sphere to sphere gluing, and the relation we had postulated is this. Now I want to write this correlation function in terms of the 3-point function on the sphere. Okay. In this case, of course, it is trivial. Everybody knows how to write a sphere 4-point function in terms of sphere 3-point function by inserting a complete set of states. Okay. But I'll write the relation in a specific way, and then it will become clear. Pardon? Oh, there is another board. Oh. Okay. Oh, below. I see. Okay. So claim this amplitude is given by Okay, ns as usual is the host number of phi s. Okay, so I'll try to give a proof. Now, see that the way I have written it here, it is more or less clear that what the structure is. That if we are trying to glue two spheres, right, we take the first sphere, write down the naive amplitude that we have, except that on the hole that is being glued, you insert a base state. Similarly, that is on the second sphere, you write down the naive amplitude, but in the hole you insert a base state, and then you glue them together by this factor over here. Okay, so this is the structure. So let me try to prove why this is the same as that I have written here. So first we shift these by A13 and shift these by A23. Okay, to write this as, now I am going to write it as a vacuum expectation value. Okay. Sorry, Z1. F of, no, right hand side should be Z2. Sorry, this Z1. Sorry, this is a, sorry, this should have been A1. I think I had written it right in the first time. So let's do this. So the claim is that the relationship look like Z1 equal to F of Z2, right? This is supposed to be the relation. Okay. So if we write it as Z1, then you can see that this gives you Z1 minus A13 equal to Q over, this is Z1. Sorry, Z2. Z2 minus A23. Okay. You could have also written Z2 in terms of Z1, which is what I had done last time, but let's stick to Z1 in terms of Z2. Okay, so this is the correct way of writing it. Okay, so in writing this, I have made a one assumption, but that is not very relevant. Okay, that I have assumed that mod AI1 minus AI3, this is larger than mod AI2 minus AI3. Okay, otherwise I have to put a radial ordering in this product. Okay, I just didn't want to write the radial ordering, so I have assumed this. Otherwise, either you have to do radial ordering or exchange the order. Okay, so now this one by definition is phi r, because that's the state operator correspondence. This one by definition is phi s. Oh, maybe I will not do this, write this as phi s yet. So then we can combine the first and the last line, because we have a complete test relation phi r c, we can replace by identity. Okay. So this, then I can write the first line, first and third line together, I can write as 0 v1 of a1 1 minus a1 3, v2 of a1 2 minus a1 3, and then an identity operator, okay, which I will not write, and then q to the L0, q bar to the L0 bar phi sc minus 1 to the ns. Okay. And for this one, okay, what I am going to do is to make a conjugation by the inversion operator I of z, which is 1 over z, okay, because that is an SL to say transformation. So I can, so correlation function is invariant under that. So I can write this as I dot phi s of 0, I dot v4 of a22 minus a23, I dot v3 of a21 minus a23. Okay. But now I am going to write this, the last line, as phi s, right, because this is the definition of the BPZ conjugate set, I dot v4 a22 minus a23, I dot v3 a21 minus a23. Okay, and I am going to now use again the second completeness relation phi s weighted by minus 1 to the ns is again identity. So this whole thing can then be written as is this okay, right? I just use the completeness relation, okay, to write it as a one single correlation function. And then the final step is to shift by a13. Okay, so that v1 of a11 minus a13 becomes v1 of a1. for this one, okay, so you see what has happened here. Okay, for the first, we shift the argument of V, okay, by A23, right? Because from A22 we have made it into A22 minus A23. So first we take Z2 to Z2 minus A23, right? Then we do an inversion, 1 over Z2 minus A23. Okay? Then we scale by Q, right? Q to the L0 is scaling, so that gets multiplied by Q. So Q over Z2 minus A23, and now I'm going to shift it back by A13. So I just add A31. Okay? So this I can write now as F dot V3 of A21, F dot V4 of A22, okay? And now I'll not even write the vacuum expression for it, so that I don't have to worry about the ordering. Okay, so I'll write the expression for F again, right? F of Z2 is A13 plus Q over Z2 minus A23. Okay, so we first shift the argument from Z2 to Z2 minus A23, right? That's the step which is already visible there. Okay. Then the inversion, okay, 1 over Z2 minus A23, okay, that's the I. Okay. Then Q to the L0 multiplies by Q, okay. And then finally the final shift that we did here, okay, to come from there to here, we add A13, and this is exactly the F that was claimed to be, or maybe I have erased it, right? Yeah, okay, here, this is the one, this is the F, yeah, okay. So this is a long way to get to 4-point function from product of two 3-point functions, right, which of course we all knew how to do, right? But now I'm going to generalize this, okay, to define correlation function on the arbitrary Riemann surface. Pardon? Some factors outside the correlation function. Yeah. So F dot this means that it's that factor. Shift doesn't do anything, right? But when you write I dot something, right, it takes into account all those extra factors that come in. It's not just shifting the argument to 1 over Z. So similarly, this F basically includes that factor. Okay. Any other question? So we generalize this. For arbitrary Riemann surface. And the rule is that anytime we identify Z1 minus A31 A1. Okay, anytime you have an identification like this, and these are the basic identifications that we use to make a general Riemann surface. Okay, we insert phi r at Z1 equal to A13, phi s at Z2 equal to A23, and multiplying by this factor over here that we saw. Okay, so I'll give an example of torus one-point function. So take a sphere with just 3 holes. So let's call this a z plane, okay. And so the holes are around z equal to a1. Let me not even write 1 or 2 because this is a single sphere. So these are the places around where these are the points around which you make the holes, okay. And identify z minus a1 as q over z minus a2. Okay. Which means that we take, let's call this a1, call this a2, and call this a3. Okay. So what we are doing is that we are taking a circle. Let's take this as mod z equal to q to the half, mod z minus a1 equal to q to the half, mod q to the half. This is mod z minus a2 equal to mod q to the half. Okay. So you are identifying these two circles, okay, on the sphere, because that's what this is telling us. Okay. And the way the identification goes, that as you move in here, from here, you move out from there, right? Because as z minus a1 decreases, z minus a2 increases. Okay. So this is a torus. Okay. And here you insert a vertex operator. Here you insert something. So this is a torus one-point function. And the claim is that this torus one-point function is obtained by starting on the sphere V at a1, V at a3, V at a3, phi r at a2, phi s, phi r at a1 and a2. Okay, so you insert basis states. Wherever you are identifying things, you insert basis states, phi r at a1, phi s of a2, and then glue them by this factor over here. Okay. So this gives you an expression for the torus one-point function. So this is torus one-point function. This is V on the torus at g equal to 1. Is this clear? So in general, you can have a complicated Riemann surface, but as you saw, all of them can be obtained by simply gluing spheres with 3 holes. Okay. And every time you glue, okay, that's equivalent to inserting factors like this. You put basis states at the holes where you are gluing, okay, and you multiply by a factor like this. Okay. So however complicated Riemann surface you have, you can always express this as products of 3-point functions on the sphere.
So, is this what you also get from string field theory?
Yes, this is essentially what you get from string field theory, because in string field theory you build from Feynman diagrams, right, and you get exactly this structure.
So regarding this question, yes, within the context variables, actually, you cannot write.
True. So here the point is that those contact terms, etc., those issues are related to what is the range of Q. Right. Here I am telling you how to construct this Riemann surface locally. Right. And then what the way the contact terms and the Feynman diagrams differ in string field theory is basically you have the same integral, but the range, certain range of Q gives you the Feynman diagrams propagators, and whatever is not covered by that range is a contact term. Right. That's the way the contact terms in string field theory arises. But as far as the correlation function of Riemann surface is concerned, you can just use this and extend Q to appropriate values. Right? It will generate the correlation function on the Riemann surface. Any other question? Okay, so using this, we can in fact also determine the Gauss number conservation on a generic Riemann surface. Okay, so let me indicate how it works here. On the torus, right? So V of A3, let's see what should be the Gauss number of V of A3. To see this, you note that in this, okay, so first of all, suppose phi s, suppose this has Gauss number nr. I'll do it here. Suppose phi r has Gauss number nr, then phi r c has Gauss number 6 minus nr, right? Because the total Gauss number of phi r and phi r c has to add up to 6 because they have non-zero nr product. Then phi s c, in order that this is non-zero, okay, the Gauss number of phi s c and phi r c has to add up to 6. Okay. So phi s c has Gauss number 6 minus nr, which is nr. So then phi s has Gauss number 6 minus nr. Okay, because it's conjugate to phi s. So what we see from here is that the Gauss number of phi s, phi r and phi s. Okay. So total Gauss number of phi r and phi s is nr plus 6 minus nr, which is 6. Right? But this is a sphere 3-point function. On a sphere 3-point function, the total Gauss number has to add up to 6. Okay. So this means that the V must have Gauss number 0. Okay. So what we learned from here is that in order to get a non-zero 1-point function on the torus, the vertex operator has to have Gauss number 0. Is this clear? Okay. So I'll leave this as an exercise. exercise for genus G, we need total ghost number 6 minus 6G for non-zero correlation function. Total, if you have a general correlation function, total ghost number of all the operators has to be 6 minus 6G. Right? So if it's a 1-point function, that particular operator has to have 6 minus 6G. Okay. And you can also verify that this, with this rule, right, the expression for the amplitude that I wrote down, okay, that has the correct ghost number as long as each external state has ghost number 2. Right? You remember you had a product of vertex operators V1 to Vn, right? And then a set of B's. Right? The B's are negative ghost number. So you can check that once the vertex operators each have ghost number 2, you have the correct ghost number of the whole amplitude. Yeah. Any question? Okay, so with this I will now start with the superstring theory. Okay, which will be following the similar kind of logic, but there are several differences that I will point out along the way. Pardon? Sphere? Oh, because last time we saw that the only way to get a non-zero correlation function, right, is to insert 3 C's and 3 C bars. Right? So that total host number adds up to 6. So that's basically the starting argument, starting point of the argument. Okay, I can do that, but maybe I can take 15 minutes because then people will get a little used to superstring theory and right. Yeah, because otherwise there will be too much stuff at one go. Okay, so superstring theory. So the basic idea for superstring theory is that you supersymmetrize the worldsheet theory. Okay, so for X mu, so supersymmetrize the worldsheet theory. So with X mu, we'll also have its pairs psi mu and psi mu tilde, left and right moving fermions. Let me call this bar because I have been using bar also. So these are these independent fermions. One is left moving and one is right moving on the worldsheet. Okay, and then you also have BC, B bar, C bar. These are the reparametrization ghosts. Okay, because we had worldsheet diffeomorphism. Okay, but now you also have worldsheet super diffeomorphism. Okay, local supersymmetry on the worldsheet, and when you gauge fix those, you get some bosonic ghost fields. Okay, Grassmann even ghost fields which we label by beta gamma, beta bar, gamma bar. Okay, so these are Grassmann even ghost fields. So I'll give the OPs. Okay, the BC X OP remains exactly the same, right? So whatever I am going to say here, okay, will have to be accompanied by whatever I had said earlier for the bosonic strings. Okay, because BC and X system is exactly the same. Okay, except for the dimension that I'm going to mention later. Okay, so I'm going to only focus on the extra fields that are appearing, which is the psi and beta gamma bar gamma bar. So OPE. So non-singular means NS means non-singular. Okay. And then there are holomorphic, anti-holomorphic parts. Okay. So I'm writing this once, but I'm not going to write it again. Okay, because whatever I'm going to write for holomorphic part will also go through for the anti-holomorphic part. Sorry, there is a 2 here, which I missed. Okay. Now, one point I should emphasize here is that in this case, if you exchange the order gamma of W, beta of Z, because they are commuting, okay, it will still remain as 1 over W, Z minus W. Right? So if you write it as 1 over W minus Z, there's an extra minus sign. Okay. This was not the case for BC, right? B of Z, C of W was 1 over Z minus W. C of Z, B of W was also 1 over Z minus W. Okay, because 1 over W, Z minus W, you can also write as minus 1 over W minus Z. Here, you have to be careful about the sign, right? I have chosen the convention where beta gamma of P is 1 over Z minus W. So gamma of Z beta of W will be minus 1 over Z minus W. Okay. Now this of course is a convention, you can change it by simply redefining your gamma, okay, but you have to stick to one convention and I'll be sticking to this one. We'll have an extra minus sign. Yeah. Extra minus sign when you write in the first minus second argument. Yes. Pardon?
Maybe it's helpful if you just write it.
Okay, okay, I'll write it. Yeah. Gamma of Z beta of W will be minus 1 over Z minus W plus non-singular. Okay, and similarly for the gamma part. Okay, so let me write down the energy momentum tensor expressions. So T psi is eta mu nu. So psi is holomorphic, psi bar is anti-holomorphic. So with this, I'll leave this as an exercise to check that psi mu, beta, gamma have weights 0 half, 0 3 half, and 0 minus half. Okay, so psi mu has weight 0 half, beta has 0 3 half, gamma has 0 minus half. Okay, this is reasonably straightforward. All you have to do is to calculate the OP of T beta gamma. Suppose you have to calculate the conformal weight of beta. You take the OP of T beta gamma with beta, okay, and then apply this OP, the OP that you already see. Okay, we also need supercurrent. Okay, so the matter supercurrent TF is eta mu nu psi mu X. Okay, so this is a fermionic partner of the energy momentum tensor. Okay. Or you can also think of this as a generator of the superconformal transformation. Okay. And with this we can write the BRST current. QB. Okay, let me write the expression for the current first. And then similarly JB bar, and QB is given by integral and QB square equal to 0 at d equal to 10. Okay, when the dimension is 10, all of these you should be able to verify, okay, by calculating appropriate OPs, right? Because I have already given all the data, right? So you have to use this expression for JB and calculate the OP of JB with itself and verify this relation over here. Okay, it's similar to what we had for the bosonic string theory, except that it's a little more complicated in this case. Okay, and you will probably recognize that these C times Tx and BC del C, these are the ones that already appeared in the bosonic string theory. Okay. In the fermionic string theory, there are extra contributions that you can see. Okay, now there is one more feature of this that I want to mention, and then we can have the break. Which is that actual CFT that underlies superstring theory is a quotient of the theory that I already described by a Z2 times Z2 transformation. Okay, so let me explain this, the action of these Z2s. So the first Z2 takes psi mu beta gamma to minus psi mu minus beta and minus gamma, and the second Z2 does the same thing for the antiholomorphic center. This basically means that in the configuration space of world sheet theory, okay, we declare that these are in fact the same points. Okay, it's like if you have the physical space, right? You may identify x with minus x. Okay, that means that these two are declared to be the same point. That's a new space. It's not the usual three-dimensional flat space. It's a space with a conical defect. Right? Here it's similar. Okay, except that this is happening in the involving the psi mu beta gamma field space. Okay, but we make identification in this field space. So this has two effects. Has two effects. First one is that all states must be Z2 times Z2 invariant. Which means the wave function of the string should have the same value at psi beta gamma and minus psi minus beta minus gamma, because these 2 points are supposed to be the same. Right? So the wave function of the string better have the same value. This is called the GSO projection. The second is that we must allow two-state boundary condition. What does that mean? That means that as we go around the string, we are allowed to have minus psi mu minus beta minus gamma, allowed to, maybe I can say, allowed to return, allowed to go from psi mu beta gamma to minus psi mu minus beta minus gamma. So if you label the string by sigma, right? So sigma is a periodic variable from 0 to 2 pi. Okay. Psi mu at 2 pi can become minus psi mu of 0. Okay, because as you go around the string, right, the psi mu changes to minus psi mu, but that's supposed to be the same point. But you have to make sure that beta also goes to minus beta and gamma also goes to minus gamma. Right? Simultaneously, you have to change all of those. Okay. And independently, you can do it for psi bar minus psi bar, beta bar, and gamma bar. So these are known as the various sectors. So let me write it here. Okay. So these lead to 4 sectors. Which are called the Nebu-Schwarz, because there are independent boundary conditions you can put on left and right. NSR, RNS, or RR. So NS means that you twist both the left and right moving formulas. Right? Psi mu goes to minus psi mu as sigma goes to sigma plus 2 pi, and psi bar mu also goes to minus psi bar mu. NSR is when the holomorphic part sector is periodic. So psi mu goes to psi mu, but psi bar mu goes to minus psi bar mu. RNS is opposite, and RR is when both psi and psi bar are periodic. Yeah, these are the levels of the spectrum. Right? I'm thinking it's just at the level of the spectrum. Right? On a cylinder, you as sigma goes to sigma plus 2 pi, this is you have to change the boundary conditions this way. Is this clear? Okay, so I think I'll stop here and then we'll continue after the break. Okay, so what we have learned so far is that in order to define superstring theory, okay, when the states of the superstring theory, we have to include twisted sectors, right? We have a GSO projection and you have to include twisted sector states, right? That's what gave rise to these different 4 sectors. Okay. So now, if you want to calculate the amplitudes involving these states, we have to insert a corresponding vertex operators, right? Because you have to understand the state operator correspondence between for the twisted sector states. Okay. And it turns out that in order to construct the vertex operators,
Can I ask a question?
yes.
So, at least like from the like action point of view, this G2 plus G2 symmetry is there in terms of in the action, that's I into minus it. So I could think of this is really some kind of global symmetry in instead of like gauge symmetries. But you want that the space has to be invariant.
Yeah. So we are lifting, we are making it into a gauge symmetry. It's up to your choice, right? So to define a consistent string theory, you have to make them into gauge symmetry, right? That's why you identify states in the configuration space related by this symmetry, and you also allow twisted sector, right? So it's exactly that you are it has a global symmetry to begin with, right? But you are now making it into a gauge symmetry. Any other question? Okay. So as I was saying, in order to construct the vertex operators, okay, so you have to construct the vertex operators for the twisted sector, and that requires us to bosonize the beta, gamma, and psi system. So vertex operator for twisted sector states require bosonizing the beta, gamma, psi system. Okay, so let me write the rules for bosonization. Okay. So for the fermions, for every pair of fermions, I introduce a bosonic field phi this way. And finally, for psi 9 plus I psi 0, that I is not there because psi 0 has the opposite signature, right? Or if you do Euclidean, then there is a I for each pair has one without I, one with I. So phi I are bosonic fields. I write down their OPE soon. So for beta and gamma, we bosonize as here xi and eta are fermionic. Xi, eta are Grassmann odd. Phi is Grassmann even. OP takes the following form. Okay, here there can be subleading on singular subleading terms. Okay, and there are similar things for the anti-holomorphic parts. And the idea is that we can reproduce the beta, gamma, and psi correlation function, psi OPs, okay, using these representations. So the point is that once you use this representation, then we use the OP that I have given here. Okay. It follows from this that the psi's have the right OP, and similarly the beta, gamma have the right OP. Okay, once you use the OPs of xi, eta, and phi. Okay. Let me write down also the energy momentum tensors. Okay, the energy momentum tensors I have already written down. Okay. So exercise, conformal weights, xi is 0, eta is 1, e to the q phi is minus half q square minus q. You can get this by taking the OP of t, xi, eta, and t phi, and just calculate the OP of this with xi, this with eta, and so on. Okay, so xi has conformal at 0, eta has conformal at 1, and e to the q phi, right, which is we'll be making use of, is minus half q square minus q. Okay. So in particular, this is 0, e to the 2 phi, e to the minus 2 phi has weight 0. Right, because for q equal to minus 2, this is minus 2 plus 2. And finally, I'll introduce another notation called the picture number. Picture number of e to the q phi will be q, xi will be 1, eta will be minus 1, and beta and gamma will be 0. Okay, this is a definition that I am going to give. So picture number is something that arises after bosonization. You see, there is no notion of picture number earlier before bosonization, because beta and gamma have 0 picture number. Okay, so they have non-zero ghost number, but they have 0 picture number. And I'll also give the ghost number, maybe in this board only. Ghost numbers will be eta 1, xi minus 1, e to the q phi will be 0. So beta minus 1, eta 1, okay. And bc of course the same, b minus 1 and c 1. Okay. So ghost number is something that was there before, right? Because beta and gamma do carry gamma. Beta and gamma do carry host number, but picture number is something which arises after bosonization, and this will be important later. Are there any questions? Okay, so what I am claiming here is that instead of using the beta gamma system, I can use the xi eta phi system, and instead of using the psi i's, I can use the phi i's. Okay, because there is a bosonization rule that allows us to express the size in terms of phi's and beta gamma in terms of xi eta phi. Okay, and the OPs, conformal weights, everything is preserved under this identification. Okay, you can check that if you use these rules, and if you calculate the conformal weight of beta, you will get 3/2, and if you calculate the conformal weight of gamma, you will get -half. Okay, because eta provides 1 and this will provide -3/2, so you will get -half. Any questions? So with this, I can now describe how to construct different sector states in the different sector. So when I say states, I will specify the vertex operators because the state operator correspondence still holds in this case. Yes.
Taking the operators psi 1 plus psi 2 and the other one on the bottom line, and I swap them, I become a sign, right?
Yeah. So the point is, what happens is if you look at the OP of e to the I phi 1 or e to the I phi 2, right, it goes as 1 over z minus w. Okay, so when you swap them, you again pick up a sign.
And I can derive this OP from
yeah, you can derive this OP from those, right? Because phi phi OP I have already given. Using that, you can calculate e to the I phi 1 or e to the I phi 1 z, e to the I phi 1 of w, and you will pick up. You will see that there is a minus sign.
You might have to be careful. You have sometimes there are cocycles.
Yeah. Sometimes there are cocycles. That happens if you have e to the I phi 1, e to the I phi 2, right? They have no singularity, right? And there you put a cocycle, right? And that cocycle basically is some matrix that multiplies the vertex operator, which has no other role but to provide a sign. Right? Imagine that e to the I phi 1 is accompanied by sigma 1 and e to the I phi 2 is accompanied by sigma 2, right? Then when you switch them, you pick up an extra sign.
Because like when you the product of like two lines, like your B is 3 or 2.
Yeah, exactly. Yeah, so between two different lines, you have to provide a cocycle factor, right? Which is like a matrix, which you, when you commute, it gives a minus sign. But for most purpose, you don't need to know what those cocycles are, right? I mean, the general OPE rules will tell you how to calculate the correlation function. Any other question? It is a good exercise to do all this because then, I mean, only then I think you can get a grasp of what's happening, right? That all the OPEs, etc., for the beta gamma system you can derive from the xi eta phi system. Okay, there is one a small point that I'll come back to that later. Okay, so now let's see how to describe the various sectors. So NS sector states. or NS sector vortex operator. Okay, states are just the vortex operator at 0 acting on the vacuum. These are given by e to the q phi for integer q times polynomial in psi mu beta gamma besides and derivatives besides x mu bc. Right. The x bc, of course, you can always use. The only place where you have to be a little careful is for the new fields. So NS sector states will be of the form e to the q phi for some integer q times polynomial in psi beta gamma and derivatives and the derivatives of these, and of course you can use all of the operators that we had used for bosonic string theory, like e to the ik dot x, derivative of x, and so on. Okay, so general vortex operator will be given by products of all these, use evaluate at 0 and act on the vacuum. That's the state. That's an NS sector state. You can have del psi mu, for example, or del beta, del gamma. Right? Just like we use del x mu, del square x mu, and so on, right? So you can take derivatives of psi, beta, gamma, right? Products of those derivatives, and apply on constructed operator, vortex operator. So anything that you want, you can do with these, right? So any polynomial in these and that derivatives. Is this clear? Right? I mean, maybe I can write some examples. Right? This is an example of NS sector vortex operator, right? E to the 2 phi, right? Q is integer, beta square gamma cube, and all this. Okay, I have not so far said what the GSO projection rule is, right? That I'll specify later. Because when you look at the OP, right, the beta gamma OPU e to the q phi, right, is single valued when q is an integer. For half integer q, right, which will be the Raman sector states, they pick up an extra factor. Okay, that's where this integer versus half integer comes in. So R sector states you have from e to the q phi, sorry, with q half integer, so q belongs to integer plus half, times okay, so basically the base is different. Here it was e to the q phi, here it is e to the q phi with q integer plus half, and then also there is this object here, you can see that this one cannot be written as a polynomial in psi, right? Because you can, if you look at the definition of where the phi's appeared, psi 1 plus I psi 2 by root 2 is e to the I phi 1. Okay. So e to the I phi 1 by 2 doesn't have a descriptor, is not a polynomial in psi, right? That's why we couldn't have written the vertex operator in terms of size. Okay, but you have to use this vertex operator. So you can write a similar expression here, except that here you can replace phi e to the 2 phi by e to the say half phi, and then you also have to use multiply by this.
So you already wrote polynomial in phi, then also you had the degree for I by 2 phi 1 plus I phi 1 to phi 1.
Yeah, so that when you multiply by polynomial in psi, it can change these coefficients. It can make it into 3 I by 2 phi 1, right, or minus I by 2 phi 1 and so on, right? But so that's why I have to allow polynomials in psi, right? But without this you cannot get from polynomial in psi. Right? That's the main point. Not all of these may be non-zero, right? Because sometimes the OPE may make it vanish. Right? I'm not saying that you can write arbitrary polynomials and it will get a non-zero result. For example, if I add b square, right? B square clearly is 0 because b is Grassmann odd. So this is general structure of what you can use.
So we have written that as some chart and phi I with chart being integer times polynomial in phi I.
Yeah, you could, but then derivatives of psi will not come from there, right? You have to also allow and derivatives of phi. Yeah, you can do that. Yeah, you could have done that. I'm saying that let's take a basic object which is constructed of phi, and then everything else you can construct in terms of the size.
Last time we introduced root number, there was symmetry. The root number was the chart.
Yes.
Now we introduce this picture number.
Yeah, there is also a symmetry associated with it. Yeah, there is global symmetry. I'll write down the picture number conservation. Again, I mean, the way we derived that Gauss number has to be 6 on a sphere, right? A similar argument we can use to show that the picture number has to be -2 in the holomorphic and -2 in the anti-holomorphic sector. Right? But I'll discuss that in a few minutes. Okay, so GSO projection. Now we have already said how the the projection operator Z2s, okay, act on the psi beta gamma, right? It changes the sign of psi beta gamma. Okay. So the only ambiguous part, right, which I have not specified yet, okay, is how it acts on e to the q phi, okay, or how it acts on this. If I tell you how it acts on this and this, then the Z2 transformation becomes clear, right? Because everything else you can derive from the fact that psi beta gamma changes sign under Z2. Okay. So to give the GSO projection rule, I have to say how the GSO projection acts on, how the GSO operator acts on these two, how the Z2s act on these two. Okay. And here the rule is the following: e to the q phi has Z is Z2 even for even phi and Z2 odd for odd phi. For even, yeah, thank you. and see this is an NS sector. In the Riemann sector, e to the q minus half phi times e to the I by 2 phi 1 plus phi 5 has GSO parity minus 1 to the q for integer q. Okay, because I have already put q minus half here. So e to the minus half phi times this will be an allowed state. E to the half phi times this will not be an allowed state. But e to the half phi times one of the sign changed will still be an allowed state, right? This you can verify because you can change one of the signs by multiplying by sin u, right? Which changes the GSO parity from plus to minus. But correspondingly, if you change q, shift q by an integer or an integer, you have a GSO even state. Is the statement clear? Okay, so exercise. E to the half phi times e to the I by 2 minus phi 1 plus phi 2 plus phi 3 plus phi 4 plus phi 5 is GSO even. Okay, because you can go from I by 2 phi 1 to minus I by 2 phi 1. You can see by multiplying it by e to the minus I phi 1, which is phi 1 minus I psi 2 by root 2. Right? E to the minus I phi 1 is GSO odd, right? Because psi 1 and psi 2 are GSO odd. So when you multiply by this changes sign, it becomes GSO odd. But you are now also changing from minus half phi to half phi, right? So q is 1. So the two GSO parities cancel, right? And we get an even GSO state. So the same story is repeated in the anti-holomorphic sector. In 2b. In type 2A theory, the GSO projection in Riemann sector, in anti-holomorphic Riemann sector, okay, and this makes the difference between type 2 and type 2b string theories. So if you go to the, so in this rule, for example, in type 2b theory, that state will be GSO odd for that will have GSO parity, not minus 1 to the q, but minus 1 to the q plus 1. Okay, so to get a GSO even state, of this kind, you have to change the number of minus signs in phi. Is this statement clear? Yeah, so this is the main difference between type 2 and type 2b string theories. Okay. How the GSO projection rule works in the anti-holomorphic Raman sector. Okay, otherwise at the worldsheet level they are identical. Now let's discuss the ghost and picture number conservations. So first, ghost number conservation is the same. It is same as in bosonic theory. Okay, so you need 3 C's and 3 C bars to get a non-zero correlation function. Picture number is a new object, right? So one has to understand how what the picture number conservation looks like. Okay. And one can easily convince oneself that the having no picture number in the conservation law is not a viable option, right? In particular, if you try to calculate the same correlation function. Let me not write the 0, just write this. Okay, this was non-zero for the bosonic string. Okay, now let's ask if this is also non-zero for the fermionic for superstring. And one can see that this is not an option, okay, because what one can do is to insert a beta of z gamma of w inside. And look at this as a function of z. It has a single pole at z equal to w, okay, but as z goes to infinity, it is supposed to fall off as z to the minus 3 because beta has conformal at 3, so 3 half, right? So as z goes to infinity, it is supposed to fall off as 1 over z cube, right? But that's not possible because it has a single pole, right? You can easily convince yourself that if you have a function with a single pole, okay, and no other singularity, okay, it cannot fall off as 1 over z cube as z goes to infinity. Okay, so this is not a viable option. This is inconsistent. Okay, because this is supposed to go as 1 over z cube as z goes to infinity, but only has a single pole. Okay. So one can do a similar manipulation to what we did last time with the ghost number, okay, and one can show that in order to get a non-zero correlation function, okay, the total picture number has to be minus 2 in the holomorphic sector and minus 2 in the anti-holomorphic sector. Okay. So the non-zero correlation function, beta gamma has picture number 0. But if you have an e to the minus phi, then beta can have additional poles, right? Beta is delta e to the minus phi, right? If you have a e to the minus 2 phi, then it has a double pole at the location of the e to the minus 2 phi, right? That double pole together with the single pole will do the job, right? So you have to, so you must have other operators in the correlation function, right, where beta has double poles, right? And picture number 2 e to the minus 2 phi does the job. Is this clear? So this is an exercise you should do, right? And the only what you will find is the only option of getting a fully consistent rule is that the total picture number has to be minus 2 both in the holomorphic and anti-holomorphic set. So the rules for the correlation function. So the basic correlation function let me also write the momentum of x then. Okay, this one I didn't write last time, but the most general correlation function should also have a to the I k dot x. So this is given by and from the various formulae for the conformal weights that I gave, you can easily check that e to the minus 2 phi has conformal weight 0. Okay, e to the minus 2 phi bar has conformal weight 0. So these correlation functions doesn't really depend on where you have put these vertex operators. You can put them anywhere you like. Okay, you get a non-zero result. Any question? Yes, if you put beta gamma here, suppose you now insert a beta of z gamma of w, right? So what happens? Beta has a single pole at z equal to w, right? And it has a double pole at z equal to y1, right? So you can take 1 over z minus w, 1 over z minus y1 square, and that does fall off as 1 over z cube as z goes to infinity. Right? So here, yeah, so you can check that this satisfies all the consistency relation. If you put a q phi, then you'll be in trouble, right? Either with beta or with gamma, you will find that it doesn't give the right behavior.
You want to introduce this beta gamma, is it like introduced as an integral over dz beta gamma about the integration about w, and then you want to start with this object.
Exactly.
This is how you're introducing.
Yeah. That suppose you have this is the property of the analytic function. The analytic function which falls off as 1 over z cube, right, has to have a certain number of poles. right? That so if you take say if it has one pole, right, it's not good enough. Are there questions? Is it clear? Right. So all I'm saying here is that if we just take beta of z, gamma of w, and if we know that this has to fall off as 1 over z cube for large z, right? If it has a single pole, 1 over z minus w, right? Then the form of the correlation function will be 1 over z minus w times a polynomial in z, right? So that as z goes to infinity, okay, will not go as 1 over z cube, right? You have to have enough number of poles for it to be able to fall off as 1 over z cube. Okay. Now there is one extra subtlety in this, right? So let me tell that also. From the way I have introduced it so far, right? This is still not completely correct. Okay. You need to insert a here is I of 0. Okay. But for most purposes, we can just avoid this, right? And we'll see why. And that's basically on every Riemann surface. Okay. Xi being a conformal at 0 field has a 0 mode. Okay. So this xi of 0, you see that everything else, I mean, if you look at the operator that I have introduced, right? Every operator has only derivatives of xi, right? Beta, eta, gamma is eta e to the phi, and beta is del xi to the minus phi, right? It all has derivatives of xi. Right? So the only place, so if you have a single xi inserted, right, that the purpose of that is to just absorb the xi 0 mode, right? It does nothing else. Okay. So for most purposes, we don't write the xi, right? We implicitly assume that there is a xi, but that the job of that is to just absorb the xi 0 mode that is there on every Riemann surface. Okay, and this will also become clear from what I'm going to say next. If you recall, for the bosonic string, when we introduced physical states, we defined cohomology. Okay. But the cohomology was defined not on the full state space of conformal field theory, but on a subspace. Okay. So we had introduced a subspace H, so that S belongs to H if B0 minus S is 0 and L0 minus S is 0, where B0 plus minus is B0 plus minus B0 bar and L0 plus minus is L0 plus minus L0 bar. Now we impose a new condition, an extra condition, and that is that xi 0, okay, let me write it eta 0. Eta 0 on the state is equal to 0. Okay. Which means, okay, if you look at the xi has dimension 0. Okay, so the expansion of xi is just xi n z to the minus n. Okay. So xi n, that means xi n on the vacuum is 0 for n greater than 1. Okay, because for n equal to 0, it's finite, right? So you don't have to impose the xi 0 acting on the vacuum equal to 0, but xi n acting on the vacuum is 0, right? Because so that it's well defined as z equal to 0. Sorry, 1. Thank you. Greater than equal to 1. So we are allowed to create states by applying xi 0. Okay. This eta 0 on s equal to 0 condition means that you don't include those states. Okay. You build your states, okay, not from the vacuum by applying oscillators of eta and xi, but not xi 0. Is this statement clear? Right. So that's an extra condition you are imposing on the state on the space on which you are going to apply the cohomology condition, on which you are going to impose the physical state condition. In terms of vortex operators, this means that we include only those vortex operators for which xi always has one or more derivatives. Is statement clear? Okay. So when you create all these GS, even vortex operators, etc., you are not allowed to use xi. You can use derivative of xi. Right? Del xi, del square xi, all of them are okay, but not xi. Okay. This is automatic in the way I have described. Okay. Because I said that you start with those states that I wrote, and you apply beta. You take polynomials and beta and gamma. Okay. Beta and gamma only involves derivatives of xi. Right? Gamma involves eta, beta involves del xi. Right? So as long as you stick to applying polynomials in beta and gamma on the basic states, you will never generate xi. Okay. So all the vortex operators, okay, come with del xi, okay, which means that when you try to write down a correlation function on the Riemann surface, okay, the zero mode that the xi has, right, has to be absorbed only by that particular xi 0 that I inserted there, right, because no vortex operator can supply a xi 0 mode, right, because vortex operators always has derivative of xi. Okay. That's the reason why that is somewhat trivial, because that always gets absorbed, right. So you can just often in your various manipulations you can just forget about that, right. So this is known as the small Hilbert space. So the small Hilbert space means that your vortex operators don't have xi without derivatives, okay, and that's automatic if you define your Hilbert space or the space of vortex operators as in the way I have described, where you start from a basic object in terms of e to the q phi and e to the I phi by 2, and then apply only the beta and gamma oscillators. Is this clear? Okay. So with this, now I can introduce physical states.
I guess you just postulated this, right? Like this is a posteriori. If we wrote this down before, we would have.
Yeah, if you had been working with a beta gamma system, right, and introduced only the picture number as through e to the q phi, then this will be automatic. Because by taking the product of e to the q phi and beta gamma, you'll never produce a xi, right? You'll always produce del xi. But yeah, if you use the xi eta phi system as the basic object, then this is an additional ad hoc condition that you have to impose. Okay, but we will see that there are other ad hoc conditions that you have to impose. Right? All of these come from the fact that when you go from beta gamma system to the xi eta phi system, right, there are some extra ingredients that come, right, which was not there to begin with. Picture number is one of them, right? Picture number had no role to play in the beta gamma system because beta and gamma have 0 picture number. Now we have introduced the notion of picture number, right? And as you will see, that will cause sufficient amount of headache, right? Which will mean that the rules of the CFT will be somewhat different from the rules that we saw earlier. Okay, because we are trying to build a CFT where it's essentially really the beta gamma which is the fundamental object, right? But we cannot do just with beta gamma, right? We have to introduce this xi eta phi system, but that has this extra ingredients that you have to remove.
Can you argue why do we need to do this modularization for the sector? Like why could not do it only phi beta gamma?
Because any polynomial in psi, right, will have will not have a branch cut in the OP with psi. Right? That's the reason why you have to bosonize it. That's one way to see that you without bosonizing you cannot really do it. Right? Because how you cannot create branch cuts, right, from polynomials. Whereas the twisted sector vortex operators will have to create branch cuts. So physical states are elements of BRST cohomology of Bose number 2. Okay, this is the same as in bosonic string theory. But if you now impose this and actually find what the cohomology elements are, what one finds is that a generic momentum the cohomology is identical in all picture numbers. This way, same physical state has infinite number of copies, right? In each picture number, there is a copy of the physical state. So there will be, so if you allow all of these as your physical states, that will for example be infinite number of gravitons. So this clearly is not something physical, right? So this and the fact that they are identical basically means that there is some kind of equivalence. That it doesn't matter what picture number you choose, you will get the same cohomology, right? So you have to choose, but the point is that you have to choose a picture number. Okay? That in order to define the space of physical states, we have to choose a picture number. So need to fix a picture number. And the canonical choice is -1 in NS and -half in Ramon. Okay, it's not strictly necessary, but it's useful because in these sectors, okay, one can show that the spectrum of L0 is bounded from below. Okay, whereas in the other sectors, the spectrum of L0 is not bounded from below. Okay, it doesn't matter because the physical states still have bounded L0. Okay, but the full spectrum in the Hilbert space in the state space doesn't have bounded spectrum. Okay, so that's why minus half 1 and minus half are useful. So, for example, in the NS sector, you will choose minus 1. In the NSR, we will choose minus 1, minus half, right? Then minus half, minus 1, and minus half, minus half. Okay? So these are the canonical choice of picture numbers with which we work, right? So the physical states will belong to these picture numbers. Okay. And the justification of this again is that the picture number was nowhere in the game when you wrote the system theory in terms of beta gamma. Right? Picture number arose after bosonization. Right? So this is an extra ingredient that has seeped in because we bosonized, right? And during this bosonization process, somehow we have gotten infinite number of copies of the original system. Okay, and now we have to try to restrict that infinite number of copies into a single copy. So let me write an example and then maybe I have to stop. Okay, okay, so this we have to impose these conditions for physical state condition. So this describes graviton, dilaton, and 2,4. Okay, you will recognize that this operator is somehow different from the operator that we had in the bosonic string theory, where there is a zeta mu nu del x nu, right? Instead of that, you have the psi bar. Okay, picture number -1 okay, as promised. The other example is here the condition is that you have to have even number of minuses. This Okay. This describes gravity-no in space-time. So the gravity-no is supposed to have one vector, one spinor index, right? The vector index you can easily see this I zeta nu, right? Spinor index basically comes from here, right? You can see that there are 2 to the 5 choices here, right? And the total number of once you impose even number of minuses, the choice is limited to 2 to the 4. Right? Those are the spinor states of this theory. Okay, so maybe I'll stop here. E to the minus, no, this is because it's RNS, right? Gravity is coming from the Raman sector on the left and NS sector on the right. Right? That's why here it's to minus 5 bar. Right? You can also do NSR, right, where this will be to the minus 5 and this will be to the minus half 5 bar, and the spinors will come from that side. Yeah, and this way you can just combine states. Yeah, sorry, x square equal to 0, and I think k nu zeta nu equal to 0. So the physical gravity-no states will have this structure. Okay, so then next time we will discuss the scattering amplitude of these, right? How to calculate the G loop endpoint scattering amplitude involving the vertex operator of the superstring theory. Okay. But we'll see that even the construction of correlation function on the Riemann surface, right, will have some subtlety, okay, which you have to discuss first, and then in terms of those correlation functions, we can go ahead and write down what the scattering amplitudes are.